So, good afternoon, all of you. So, in the last class, we have started air refrigeration, and in that we have discussed the ideal cycle of air refrigeration, that is the reversed Carnot cycle, and the practical cycle is Bell-Coleman cycle. Okay, or you can call that as also Brayton cycle. Okay, reversed Bell-Coleman cycle or Brayton cycle. And we have seen that Carnot cycle is not practicable. Okay, so why it's not practicable is, so the isentropic processes, compression and expansion should be always, so those should be always at high flow rate. So with high speed, those two operations should be done, and the remaining heat rejection and heat abstraction should be at very low rate. So that's why it's not practicable, but the efficiency or the coefficient of performance of the air refrigeration with reversed Carnot cycle is maximum. And the practical cycle we have seen is Bell-Coleman cycle. So in that already we have seen air refrigeration. The main four components required are compressor, then condenser or a heat exchanger, then an expander. So the main four components required for air refrigeration are compressor, condenser, then expander and the evaporator. So evaporator is nothing but the space where exactly the cooling effect is required. And we have derived that the COP of reversed Carnot cycle is the ratio of the lower temperature to the difference between the two temperatures. So higher temperature and lower temperature. And we have seen some two examples when the same cycle is used for air conditioning and also for refrigeration. We have seen that always the air conditioner will work with more COP than that of the refrigerator. And even for seasoning also, in summer and winter, if you compare the same cycle, always the COP of the winter air conditioner will be always greater than that of the summer air conditioner due to the high temperature in the atmosphere. And already we have seen the Bell-Coleman cycle. So the four operations already we have seen. So compression and expansion are assumed as isentropic, but these are not isentropic and these are polytropic. Then heat rejection and heat abstraction. So these are at constant pressure. So those are isobaric process. And we have seen the COP also. And in addition to that, what we have seen is we have discussed some problems on reversed Carnot cycle. So let us come to the next lecture of air conditioning, air refrigeration, that is. So again, see the reversed Brayton cycle or the Bell-Coleman cycle here. So 1 to 2 is compression, 2 to 3 is heat rejection in the condenser, and 3 to 4 is isentropic expansion in the expander, and 4 to 1 is the actual refrigerating effect produced by taking the heat from the space to be cooled. So the main four components with PV diagram and TS diagram you can see from this figure. So let us see the COP of the Bell-Coleman cycle. So already we have seen that COP is the ratio of the refrigerating effect produced to the work input. So in this, some work is done by the expander, so that work can be reduced from the work required by the compressor. The refrigerating effect is nothing but the heat to be removed from the space to be refrigerated. So which is equal to Cp into T1 minus 4, where T1 is the temperature that is required, and T4 is nothing but the temperature of the refrigerant coming from the expander. Then the work input is nothing but work required by the compressor minus work done by the expander. So assuming that this is an isentropic process, we can write this as gamma into, so P2 V2 minus P1 V1 by gamma minus 1. So that is the work required by the compressor minus work done by the expander. So that is gamma into P3 V3 minus P4 V4 by gamma minus 1. So where 3, 4 is nothing but the expansion process. So we can write the work input in terms of gamma R and only the temperature instead of the pressures and volumes. We can write this as gamma by gamma minus 1 into R into T2 minus T1 minus R into T3 minus T4. So we can write that as, because so Cp is gamma R by gamma minus 1, we can write the total network required as Cp into the difference between only the temperatures. So T2 minus T1 minus T3 minus T4. So already we have seen that compression process and the expansion process are assumed as isentropic. So here the maximum pressure is P2 and the minimum pressure required in the cabin is P1. So T2 by T1 is P2 by P1 to the power of gamma minus 1 by gamma. And also the process 3-4 is also isentropic expansion process. So we can also write that T3 by T4 also equal to, so maximum pressure by minimum pressure to the power of gamma minus 1 by gamma. So from the equations 2 and 3, so because here T2 by T1 is same as T3 by T4, because only the two pressures maintained are P2 and P1 only. So we can write COP as Cp into T1 minus T4 by Cp into T2 minus T1 minus T3 minus T4. So if you write this in terms of 1 by T2 minus T3 by T1 minus T4 minus 1. So we can also equate T2 by T3 is equal to T1 by T4. So we can subtract 1 from left hand side and also from the right hand side. So from that we can write that as T2 minus T3 by minus 1 is equal to T1 by T4 minus 1. So from that we can say that T2 minus T3 by T1 minus T4 is T3 by T4. Okay. So if you substitute this in the COP relation, we can get this as 1 by T3 by T4 minus 1. So that is COP of the reversed Brayton cycle or the Bell-Coleman cycle is nothing but T4 by T3 minus T4. So that is the relation when we assume compression and expansion are isentropic and the pressures are also P2 and P1 only. There is no pressure drop during condensation or there is no pressure drop during heat abstraction also. So if we assume, so that is the isentropic expansion, isentropic compression. So these are not possible in this cycle also. So always it will be polytropic process only. So we can write network required in terms of N, polytropic index N. So that is N by N minus 1 into gamma minus 1 by gamma into Cp into the difference between T2 minus T1 again minus T3 minus T4. So we can write COP as T4 by so we can write that as in terms of T4 by T3 minus T4 into N by N minus 1 into gamma minus 1 by gamma, where N is the polytropic index. So that will be always greater than that of gamma. So that is the relation for COP of the cycle. And already we have seen the COP of this cycle will be always less than the COP of the reversed Carnot cycle. So already we have seen that air refrigeration is again of two types, open system and the closed system. So in the open system, so the exhaust is sent into atmosphere, where in the closed system, air used is circulated throughout the cycle. So closed system is also called as a dense system. So the main disadvantage of open system is that, so there is always possibility of choking of the valve, expansion valves. Okay. So that because here the air directly takes the moisture from the fruits or whatever the vegetables that kept inside the refrigerator, and while expansion here, so that will be carried along with that moisture will be carried, and due to that here always there is possibility of choking of the valve, so that can be avoided in the closed system. So you can see the figure of the closed system or the dense system. So in this there is a heat exchanger. So in that another fluid is used. That fluid may be brine solution. So whatever the air expanded from the expander goes through this heat exchanger. So heat exchange will take place from the air to the brine solution. So whatever the air that is coming at low temperature and pressure from the expander, so that will be used for cooling the brine solution, and only the brine solution is passing through the evaporator that is to be refrigerated, and here it will take the heat from the refrigerator, and finally the same brine solution will be again coming into the heat exchanger through a pump. Okay, that brine solution is only confined to this circuit, that is the heat exchanger and the evaporator. So whereas air is confined only to compressor, then condenser, then expander. So air is not directly coming into the refrigerator or the evaporator to be refrigerated. So using the closed system or the dense system, there are number of advantages. So one advantage already you have seen that. So there is no choking of the valves because air is not directly going inside the refrigerator and that is not taking any moisture from the refrigerator. Then the other advantages you can see is the desired pressure. So the exit pressure will be always above the atmospheric pressure. Whereas in the open system, because the exhaust is going into atmosphere, so always that minimum pressure should be always the atmospheric pressure only. Whereas in the dense system, we can maintain this lower pressure greater than the atmospheric pressure. And the other advantages are that the specific volume and total volume of the air are reduced, which will reduce the size of the compressor required and also the expander required for the same capacity of the open system. So the main advantages are that there is no choking at all and the pressure can be maintained above atmospheric pressure. So due to that here the size of the components, mainly compressor and the evaporator, can be reduced. Then let us see the aircraft refrigeration. So aircraft refrigeration also, the cycle on which it depends is again the Bell-Coleman cycle only. So you can see what are the various heat sources. So when the aircraft is moving at high velocity in the space at high altitude, so where the pressure will be less and even temperature should also be less, because at high altitude both will be less. But in the cabin, so we have to maintain nearly atmospheric pressure. So for maintaining that itself, so number of heat sources are there. Okay. So air resistance will be there when the vehicle or the aircraft is moving. So air resistance will be there, and because the aircraft is moving at high velocity, whatever the air that is coming inside the vehicle or inside the aircraft will be at a high pressure and also temperature. That effect is called as the ramming effect. So ramming is nothing but the increase of pressure and temperature of air because the air is moving at high velocity. So here the kinetic energy, whatever the kinetic energy produced due to this will be taken away for increase of the pressure. Then also number of occupants will be inside the aircraft. So the heat will be liberated by each occupant. So that will also increase the temperature inside the aircraft. And also the surface of the aircraft is exposed to sun energy. So due to that also the temperature will be increased. If some windows are there, through windows also some solar energy will go inside the cabin. So that will heat the complete aircraft. So here, for maintaining the required comfortable temperature, so that is 22 degrees centigrade, and for food preservation and all those, so minus 5 degrees centigrade is required. So for that, whatever the heat that is added should be removed. So here, what are the loads acting? You can see the air resistance and heat liberated due to fast moving air relative to the plane, and also ramming. So ramming here is nothing but increase of the pressure and temperature due to the speed of the vehicle. So vehicle here is an aircraft. So at a velocity of 300 meters per second, you can see the example at a velocity of 300 meter per second and the temperature at 10 degrees centigrade and the pressure 0.3 bar. So let us assume that these are the cases taking at when the vehicle is moving at some 10,000 meters altitude. Okay. So in that case, the temperature rise will be around 40 degrees centigrade. So when the vehicle is moving at 300 meters per second, so even though the vehicle is moving at a low pressure and low temperature, so the temperature of the vehicle will be raised by 40 degrees centigrade. So the temperature should be reduced and the pressure should be increased. And whatever the electronic appliances or electrical appliances used in the cabin or the aircraft, so that will also add some heat. And you can see the medium sized plane, the power consumed is around 10 to 15 kilowatt. So with that equipment, electronic and electrical equipment, so the temperature will be increased by 45 degrees centigrade. So what is the necessity of cooling of the airplane or aircraft? So we are thinking that at high altitude the temperature will be less and there is no need of even cooling also. But always we have to maintain the comfortable temperature of 22 degrees centigrade, and for food preservation the temperature required is minus 5 degrees centigrade. So because here at high altitude the temperature is very less and pressure is also very less, so many heat sources are there. So we can classify the heat sources on the aircraft as external heat sources and also internal heat sources. So you can see the external heat sources. These are the external heat sources, because here the surface of the aircraft is completely exposed to the sun energy here. So the solar heat gain through windows and the top surface of the plane. So that will add some heat to the aircraft. And also heat generation due to skin friction caused by the fast moving aircraft. So when the vehicle is moving at high velocity here, so always opposite to the air here, so the temperature and pressure will be increased. So whatever the air coming inside the cabin will be at high pressure and also temperature. So that should be reduced. So at high altitudes, the outside pressure will be always lower than atmospheric pressure, maybe 0.2 bar, 0.3 bar. So that depends upon the altitude at which the aircraft is moving. So for example, when you see that outside air is at a pressure of 0.2 bar and a temperature of 223 Kelvin. So at an altitude of around 10,000 meters. Okay. So due to this, when the required pressure is 1 bar here and the temperature required is 22 degrees centigrade. So here the temperature will be increased by 40 degrees centigrade. Similarly, when the aircraft is moving at at an atmosphere of 0.8 bar, then the temperature will be increased by 332 degrees centigrade. Kelvin, that is 332 Kelvin. So around 50 degrees centigrade rise will be there. So this effect is called as the ramming effect. So ramming is nothing but, so the air which is coming inside the cabin will be so pressurized. So that pressure and temperature will increase. So automatically, because the vehicle is moving at a very high velocity. So which will increase the heat. So that is one of the external heat source. And the last point, you can see that the solar radiation for low speed aircraft flying at low altitudes need not require cooling system or refrigeration system, but when it is moving at very high velocity, so always a cooling system is required. So the main external sources are solar heat gain, then the ramming effect, and always due to the surface temperature. Then these are the internal sources. So inside the aircraft, so number of people are sitting, so they will give out heat. So the sum of the heat given out by the number of people will increase the temperature inside the aircraft. Then heat liberated by the electronic equipment for the control system. So number of lights are there, number of controlling equipment are there, which will add heat to the aircraft. So that heat is to be removed. Then engine parts. So you know that aircraft depends upon the movement of the aircraft depends upon the gas turbine. Okay. So here jet propulsion you have studied in thermal engineering too. So in that you have seen that engine will be working only due to the two laws, that is Newton's second law and third law. Okay. So which requires a gas turbine and also nozzle. So in the gas turbine it requires a compressor, then a combustion chamber, and then compressor, combustion chamber. What is the next one? Turbine. Okay. So in the compressor, so the air is compressed and afterwards the heat is added in the combustion chamber. Then the gas is at high pressure and temperature. When these are expanded through a turbine, we will get some work. Okay. So that work is nothing but here. So that work, and afterwards what will done here? So nearly the work done by the turbine is utilized for running the compressor only. Okay. So propulsion of the vehicle will be only due to the expansion of the remaining gases in a nozzle. Okay. So propulsion will be coming when a jet of high speed jet coming from the nozzle. So the propulsion will be always in the opposite direction to that of the nozzle. So this aircraft also here will be having a compressor, then a combustion chamber, and then a turbine. Okay. So due to all these engine parts also, aircraft is subjected to high temperature, and that is to be removed for comfort air conditioning. So for designing the aircraft, what are the factors to be selected for the mainly the refrigeration system? So we are confining only with respect to the refrigeration system and not with respect to the propulsion of the engine, aircraft engine. So what are the loads? Those are to be considered are the engine load. So engine load is represented by WE, so which is called as the live load, and the fuel load. So the fuel is always required. So whatever the fuel that is taken is called the fuel load. And dead load or the payload. So dead load or payload is nothing but the number of occupants inside that aircraft and the aircraft structure also. Okay. So the three loads which are required for designing of air conditioning system or refrigeration system is WE, that is the engine load, fuel load, and the dead load. So here, so an aeroplane is designed for minimum WE. Okay, engine load should be at less and also with minimum fuel consumption. So WE should be less, and even WF, that is the fuel load, should also be less for the given WP. So WP is nothing but dead load is always constant, number of occupants inside and the structure. So that is constant. We can able to reduce only WE and WF. And also the other factors on which the refrigeration plant depends is the running cost of the refrigerating plant, the investment cost due to increase in engine weight to carry the refrigeration plant, and fuel consumption cost. Okay, so the total cost of the plant per ton of refrigeration is nothing but so running cost, then the investment cost, and the running costs or the fuel cost. So fuel cost or the investment fuel cost, then investment cost due to increase in weight and all this. So here, if you see that the total cost per ton of refrigeration should be always less. So when it will be less is whenever the running cost is less and the fuel cost is less. So that the engine investment cost is always fixed. We cannot change that, and the running cost should be less and the fuel cost should be less. Then in the vapor compression refrigeration system, which is used, okay, which will be having only the running cost. So there is no engine investment cost or the fuel cost. So why air is used as the refrigerant? Already we have seen in the last class. So again in aircraft refrigeration, air is only used, even though the COP is very low, but here it is used as a refrigerant because here air is cheap, safe, non-toxic, non-flammable. Already we have seen the number of advantages of air refrigeration system. Even though there is leakage is there, so it does not affect. And the cold air can be directly used for cooling, thus eliminating low temperature heat exchanger. Okay, so mainly this is for the open system. And design of the complete system is much more simpler due to low pressure. So maintenance cost is also less. So why here air is used as a refrigerant in aircraft refrigeration is, so even though this aircraft is moving at a very high velocity, high altitude, at low pressure and low temperature, so here for comfort of the human beings, always here the air is to be conditioned, or it is to be, so it should be maintained at the required comfortable temperature. So because already the vehicle is having compressor, combustion chamber and a turbine here, so that will increase the pressure. Okay, compressor is mainly for increasing the pressure. So that compressed air can be used for air refrigeration. So that's why here, so the air refrigeration is an important, plays an important role in aircraft refrigeration, even though the COP is less, because there is compressor, there is turbine inside the engine. So this reduces the weight of the equipment per kilowatt cooling considerably than 50% of an equivalent vapor compression equipment. So because already compressor, turbine, everything is there, so which will reduce the weight of the system. Okay. So whereas if vapor compression refrigeration system is directly used in aircraft refrigeration, so in that case, so the weight will be increased double. Then let us see the various types of aircraft refrigeration. Okay. So there are 5 types. So that is simple cooling system, simple evaporative cooling system, then bootstrap cooling system, then regenerative cooling system, then reduced ambient type cooling system. So these are the various systems used at different speeds. Okay, when the vehicle is moving at very high velocity, more than Mach number of 1.5 or 2.5, then in that case one type is suitable. If it is moving at a lower velocity, then one type is suitable. Let us see all these in detail with the flow diagrams and the TS diagrams. So this is the simple cooling system. So this system was discovered during 1920 to 42, which was used previously. So this can be used when the Mach number is between 0.2 to 0.65. So when the vehicle is moving at a low velocity compared with that of the remaining. So in the simple cooling system, you can see the flow diagram. So consisting of compressor, combustion chamber, then a turbine. So that is mainly for running of the engine of the aircraft. Okay. So whatever the diagram below that shows the refrigeration system required for the aircraft. So here you can see the ambient air coming inside that will be coming as the rammed air. So ramming effect is caused due to the movement of the vehicle. Okay. When the vehicle is moving in the air at high velocity, so around that vehicle here, the pressure and temperature of the air will be increased, and that air will come inside the engine. Okay, that is called the rammed air. So in this simple cooling system, so apart from combustion chamber, compressor and turbine, the other equipment required are the heat exchanger and a cooling turbine and then a fan. So you can see this one here in the flow diagram. So whatever the compressed air coming from the main compressor, a part is used for refrigeration and the maximum part will go into the turbine itself. Okay, for expansion of the turbine to get some work done in the turbine which will be used for running the main compressor itself. So for the air refrigeration here only a part is used here. So that small current of that compressed air from the main compressor goes through a heat exchanger. So in the heat exchanger the cooling is done. So how the cooling is done? So it is at constant pressure and what is the fluid used is nothing but the rammed air itself. Okay. So the rammed air is used for cooling that because here the vehicle is not moving at very high velocity. Whatever the ram air coming inside that will be at a lower temperature, not at a very high temperature. So that can be used as a sink for absorbing the heat from the heat exchanger. So like that the heat rejection is taking place at constant pressure. Then after that heat exchanger, the air at low temperature so will be expanded through a cooling turbine. So here in the cooling turbine some work is done. So that work is utilized for running the fan. So that fan will be used for so taking the rammed air. So the rammed air passes into the heat exchanger and with that the cooling effect is produced and finally the exhaust from the fan is nothing but again the ram air into the atmosphere. So in the cooling turbine after expansion, so whatever the refrigerant that is coming is at low temperature and pressure. So that will be sent into the cabin to be refrigerated or to be cooled. Okay. So that is the pressurized and air cooling cabin. So where here heat will be abstracted from the cabin by means of this refrigerant at low pressure and temperature and then that will go into the atmosphere. Okay. So that is a flow diagram. So mainly consists of a heat exchanger. So here the heat exchanger is nothing but air to air heat exchanger only. Okay. So whatever the compressed air coming here will be cooled by the rammed air itself. So that heat exchanger is a air to air heat exchanger. And the work done by the cooling turbine is utilized for running the fan. So that fan is operated by the cooling turbine itself. So to draw this rammed air and to send this rammed air which is coming as hot air. And the same thing you can see from the TS diagram. So this is again a Bell-Coleman cycle. So 1 to 2. So 1 is nothing but the atmospheric pressure. Okay. So at that high altitude, whatever the pressure that is nothing but here 1. So 1 to 2 assumed as ramming. That ramming is assumed as isentropic compression. The ramming effect is the compression of the atmospheric air to 2. Then 2 to 3 is nothing but actual compression in the main compressor. So where here the pressure is increased. So 3 is nothing but the maximum pressure and also temperature of that cycle. And 3 4 is the heat rejection in the heat exchanger. So that is air to air heat exchanger only. So it is assumed as isobaric. 3 to 4 is heat rejection, which is isobaric heat rejection. And then here the refrigerant, that is nothing but air will go into the cooling turbine where expansion is taking place from 4 to 5. 4 to 5 is the isentropic expansion. So the work done by the cooling turbine is utilized for running the fan. So 5 is the temperature of air which is at low pressure and temperature, which will take the heat, and finally so that will go at a temperature into atmosphere at somewhere 6. Okay. So after 5 you will get 5 6. 6 is nothing but the exit from the cabin. Okay. So that will be always greater than 1, but it will be lower than 2. So you can see the TS diagram. So TS diagram 1 to 2 is compression due to ramming, and 2 to 3 is compression in the main compressor, and 3 to 4. 3 to 4 is nothing but heat rejection in the heat exchanger, and 4 to 5 is entropic expansion in the cooling turbine. So 5 is the state of the refrigerant, so which is at low temperature and pressure that goes into the cabin to be refrigerated or to be cooled. Then the exit from the cabin, so will be at a 0.6. So that is not shown in the figure, but that 0.6 will be always over the same pressure line. So with this simple cooling system, so this is mainly used when the aircraft is not moving at very high velocity but at a low velocity. You can find out what is the work input to the compressor. If you know the mass of the air coming from this compressor and the specific heat of air, then the difference between T3 and T2, because T3 is nothing but the main compression in the main compressor. So the work required by the compressor here is MCP delta T. The delta T is nothing but T3 minus T2. So here we have not taken the work done by the cooling turbine, because here the work done by the cooling turbine is utilized for running the exhaust fan only. Then also we can find out the mass of air required for this refrigeration or for cooling. So that is, if T is the tonnage of the system required, then it is 3.5 into T by, so Cp into delta T. That delta T is nothing but T6. T6 is the state of the air coming out of the cabin. Okay, that is going into the exhaust, minus T5. So T5 is the minimum temperature of the cycle, okay, where the refrigerant is at very low pressure and temperature. So with all this you can find out the COP also. If you know T tonnage, 3.5 T by work input to the compressor. So that will give out the COP of the simple cooling system. Then the next type is simple evaporative cooling. The same thing is given with some wording here. So this is nothing but an open system. Then what is T1, T2, what is ramming, then 2, 3 compression, 3, 4 heat rejection, then all this 4, 5 again. So isentropic expansion, all this. So this system is good for ground cooling. So when the air is not, when the vehicle is not moving, okay, as fan can contribute to maintain airflow over the air cooler. So this system is can be used on ground cooling, because here the ramming effect produced is very less. Then the second type is simple evaporating cooling system. So you can see the additional component in this. So the main compressor, main turbine, everything is same here, combustion chamber. Then there is heat exchanger similar to the previous one. And in addition to that, there is an evaporator. Okay. So here this type is used when the exhaust from the cooling turbine is at a higher temperature. So always we have to get T6 at very low temperature. Okay. So if at all some T6 is at higher temperature, then an evaporator is installed between a heat exchanger and a cooling turbine. And in the evaporator, so some other liquid is used, not air here. Okay. So the first heat exchanger is nothing but air to air heat exchanger, whereas evaporator, so here the sink used is nothing but liquid of water or otherwise ammonia or alcohol, so which are having a very low boiling point at high altitudes. So you know that at some 10,000 meters altitude, so water will boil at 40 degrees centigrade itself. So whereas at atmospheric pressure, it will boil at 100 degrees centigrade. So like that, so another liquid is used. So that may be water or ammonia or alcohol. So here a part of the compressed air from the main compressor is cooled in the first heat exchanger. So for this, the heat rejection is to the rammed air itself. So the rammed air is used for used as a heat sink here, and with that the cooling is done here. Then again that cooled air is again passed into an evaporator where further cooling is also done here. So then it goes into the cooling turbine where here expansion is done. So work done by the cooling turbine is utilized for running the exhaust fan. So that fan will handle the rammed air. Okay. So from the cooling turbine, because the refrigerant is at low temperature and pressure which can take heat from the cabin to be cooled, it goes into the cabin and it will take the heat and it is rejected into atmosphere. So you can see the TS diagram also. So 1 to 2 is, so 1 is nothing but the ambient pressure, 1 to 2 is ramming. Okay. So the rammed air will go into the actual compressor at 2. So actual compression is isentropic, which is from 2 to 3. Okay. So 3, 4 is the heat rejection in the 8 to 8 heat exchanger, whereas 4 to 5, the process 4 to 5 is the heat rejection. So with the brine solution or water or alcohol. So with that 5 will be still at a lower temperature. Then at the point 5 here, the air goes into the cooling turbine where expansion is taking place. So to 6. So 6 is the point at which the refrigerant will come out at low pressure and temperature that goes into the cabin to be conditioned. And with this here, you can find out the mass of the liquid required in the evaporator. How much mass of the liquid, that is either water, ammonia, or alcohol. So that is to be used in the evaporator for further cooling during the process 4-5. So which is nothing but Q into T by HFG, where Q is nothing but, so Q is the heat rejected and T is nothing but the time of the flight. Okay? The flight in which period it is moving. T. Okay? And HFG is the latent heat of that liquid. So with that Q is the total heat to be removed in the evaporator. So that should be multiplied with the flight travel divided by the latent heat of the liquid used. With that we can find out how much quantity of mass of that liquid is required in the evaporator. So similar to the previous one, here also we can find out what is the total mass of air required for air conditioning, okay, or for cooling. So which is again 3.5 into T into Cp into T7 minus T6. So at 6 here the refrigerant air goes into the cabin to be cooled and finally the air will go into exhaust at 7. Okay, so that's why that temperature should be considered for. So the mass of the refrigerant required 3.5 T Cp into T7 minus T6. And what is the work input to the compressor? So in this also work done by the cooling turbine is utilized for only running the exhaust fan. So only the work required for compressor here is mCp into the process, compression process is 2 to 3. So that is T3 minus T2. So with this you can find out even COP also. So that is 3.5 T by work input to the compressor. So using this, the main advantage here is, so the exit temperature from the cooling turbine, so that is 6 will be lower than that of the previous. So the lower the temperature, the more heat can be taken away from the chamber to be cooled. Then the other type is bootstrap refrigeration system. Okay. So this bootstrap refrigeration system is used mostly for transport type aircrafts, and the main difference between the previous one and in this one is, so there are two compressors required. One is the main compressor, then the other is the secondary compressors, and also there are two heat exchangers required. So in the simple cooling system you have seen only one heat exchanger, whereas simple evaporative cooling system there is another evaporator added. So whereas in this case there are two compressors required and two heat exchangers required, and again there is another cooling turbine also. So the cooling turbine is used for running the secondary compressor. So you see the flow diagram. So when the ambient air comes inside the vehicle, it will be rammed air. So that rammed air itself is used for heat rejection. So a part of the compressed air from the main compressor first passes through the primary heat exchanger. Okay. Then so it passes through the primary heat exchanger, where here the rammed air itself is used for heat rejection. Okay. Then after the heat rejection in the primary heat exchanger, so it passes into a compressor, where here the air is again compressed in the secondary compressor, and afterwards at high pressure and temperature, when it is passed through the secondary heat exchanger, so here also the heat rejection is taking place to the rammed air itself, and then the air from the secondary heat exchanger, when it is expanded in the cooling turbine, so that some work is done in the cooling turbine, that work is utilized for running the secondary compressor. So in this there is no need of any fan. Okay. So whereas in the previous one fan is used, so whereas here the rammed air is coming at high pressure such that the difference in the pressure itself will maintain to exhaust the ram air. So that's why here there is no need of fan. And the other observation you can see, there is another compressor. So the function of the compressor is again to increase the pressure and temperature, and the heat rejection is taking place in the secondary heat exchanger. Then at point 6 it is expanded in the cooling turbine. So the work done by the cooling turbine is utilized for running the secondary compressor. Okay. So that the exhaust of the cooling turbine, the refrigerant will be at the low temperature and pressure. So that can be sent into the cabin, where here the heat abstraction or the refrigerating effect is produced in the cabin. So the same thing you can see in the TS diagram also. So 1 is the atmospheric pressure, you can see 2 is the cabin pressure, and 3 is nothing but, so outlet pressure from the compressor 2. Then it goes into, so 2.5 is nothing, 4.5. 4.5 is nothing but again compression in the secondary compressor. Then 5-6 is heat rejection in the secondary heat exchanger. Okay, the processes here you can see 3-4 and 5-6. So both are heat rejection. The first primary heat exchanger, then in the secondary heat exchanger. Then 6-7 is the actual expansion in the cooling turbine. So the work done by the cooling turbine is utilized for running the compressor. Okay. So by this way we can get 7 at very low temperature and pressure compared to the previous two, simple cooling system and also simple evaporative cooling system. And here in this all the process we have assumed as the ideal process. So 1 to 2 is isentropic compression, then 2 to 3 is again isentropic compression in the main compressor, then 3-4 is ice heat rejection in the primary heat exchanger. So here the sink is nothing but here the ram air itself will be used as a sink. Then 4-5. So 4-5 is again the compression in the secondary compressor. So with that we can able to increase the pressure and temperature, and here the work available from the cooling turbine itself used for running the secondary compressor. And again 5-6 is nothing but again heat rejection in the secondary heat exchanger. Here also the rejection is to the rammed air itself. Then 6-7 is isentropic expansion in the cooling turbine. Okay, so with that the compressor 2, so second compressor or the secondary compressor is run. So the refrigerant coming from the cooling turbine is at 7, which is at low pressure and temperature compared with the previous two. So that will take the heat from the cabin to be cooled. And finally, so the air comes into the exhaust at 8. Okay. So 7-8 will be again constant pressure process. So 8 will be between 1 and 2. So here also you can find out what is the mass of the air required. So that is 3.5 into T by. So Cp of air into the difference between the two temperatures. So that is T7 is the exit from the cabin and T6 is of the air goes into the cabin. And work input to the compressor. So work input to the compressor here is mCp into T3 minus T2. That is for the main compressor is. Okay. The work input to the main compressor. So whereas the work input to the secondary compressor is 0. Okay, because here the work is given out by the turbine itself. So with that you can find out even COP of the bootstrap air refrigeration system, which is 3.5 T by WC. So similarly there is bootstrap evaporative cooling system. So in the bootstrap refrigeration you have seen there are 2 compressors and then 2 heat exchangers and all this. In the same way here, so there is one more heat exchanger. So that is nothing but the evaporator. So here you can see here the rammed air itself is used for cooling the primary heat exchanger and the secondary heat exchanger. Okay. So here the compressed air from the main compressor first passes through the heat exchanger 1. Then afterwards it goes into again the secondary compressor. Again it goes into the secondary heat exchanger. Then it goes into the evaporator. Okay. So in the evaporator, so a liquid is used. It may be water or alcohol or even nitrogen can also be used. Okay. So with that the refrigerant goes into the cooling turbine for further expansion, and the work done by the secondary turbine is used for running the secondary compressor, and then the refrigerant coming from the cooling turbine, which is at low temperature and pressure, goes into the cabin to be conditioned. So you can see the same thing from the TS diagram. So everything is same, only the difference here is The heat rejection is taking place in the secondary heat exchanger and also in the evaporator. Whereas in the previous one, there is no evaporator. Okay. So with this system, we can able to get the exhaust temperature from the turbine still lower than the bootstrap cooling system. So you can see the processes. So 1 to 2 is ramming, then 2 to 3 is compression in the main compressor, then 3 to 4. So 2 4 is heat rejection in the heat exchanger 1. Then similarly 3 4. So 3 4 is the heat rejection in the heat exchanger 1. Then 4 5. 4 5 is the compression process in the compressor, and 5 6. So 5 6 is the heat rejection in the secondary heat exchanger. So for this also, for cooling of this also, rammed air itself is used. Then 6 7. 6 7 is again the heat rejection. So with some other fluid carried in the aircraft. Then 7 8 is the isentropic expansion in the second turbine to get the work required for running the compressor. Okay. So 8 is the state of the air at low pressure and temperature. So that goes into the cabin to be refrigerated, and finally it will come out at 9. Okay. So 8 is the inlet to the cabin. So 9 will be the exit from the cabin. So with this also you can find out what is the mass of the refrigerant required. So that is 3.5 T by the difference between the two temperatures of the air. So that is T9 minus T8. Okay. So with this you can find out even the work required in the compressor. Okay. The work is given only in the work is required only for the first compressor. Okay. That is during the process 2 to 3. So you can find out what is the work input to the first compressor as MCP delta T. So the delta T is T3 minus T2. And there is no work required for the secondary compressor because the work done by the cooling turbine is utilized for running the secondary compressor. So using this, the main advantage is that, so at 8, the state of the refrigerant at low pressure and temperature compared with that of the previous system. So this is another cooling system called as the regenerative cooling system. So this regenerative cooling system is used whenever the turbine exit will be at a higher temperature. Okay. So if the cooling turbine discharge temperature of a simple system is high, then a regenerative system is used. So you see the flow diagram here. So in this, the only difference here is that, so some of the exhaust from the second turbine, that is the cooling turbine, is used for heat rejection in the regenerator. Okay. So there are two heat exchangers. The first one is air to air heat exchanger, just like the previous one. So whereas the second one is again air to heat exchanger, but the difference here is the exhaust from the cooling turbine is used for cooling the refrigerant coming from the first heat exchanger into this. Okay. So, and in this, a part of the compressed air from the main compressor passes through the primary heat exchanger, okay, where the heat rejection is by the rammed air itself. Okay. Then the air goes into the another heat exchanger that is called as the regenerator. So why it is called as regenerator means the exhaust from the cooling turbine is used for cooling that air. Okay. Then the air, after giving the heat to the regenerator, then it is again expanded in the cooling turbine for further cooling. Okay. Then afterwards, so the from the cooling turbine, the air is at low temperature and pressure, so which will go into the cabin, and a part of that is again used into the heat exchanger for cooling of the air. So here you can see from the TS diagram also. So 1 to 2 is the ramming here, and 2 to 3 is actual compression in the main compressor, and 3 to 4 is the heat rejection in the primary heat exchanger. Then 4 to 5 is heat rejection in the regenerator. So here how the heat rejection is taking place in 4, 5 is nothing but by using the exhaust air from the cooling turbine. Then 5 is at the inlet of the turbine, and 6 is the, so 5, 6 is isentropic expansion in the cooling turbine. So here in this, so the air at 6, okay, is used for cooling the regenerator. So the same thing is again going into the cabin to be cooled. So with this you can find out the mass of the air passing through the cabin, and the mass of the liquid or the mass of the exhaust used from the turbine also you can find out. Okay. So you see the TS diagram. So 1 to 2 is the ramming effect, because here the vehicle is moving at supersonic velocities. So this ramming effect will be more. Okay. Then 2 to 3. So actual compression in the main compressor, and 3 to 4 is heat rejection in the primary heat exchanger, and then 3, 4 is 4 to 5 is the heat rejection in the regenerator, and 5 to 6, 5 to 6 is the actual expansion in the cooling turbine. So with this we can get some work. That work is utilized for running the fan. So that fan will draw the hot rammed air, so that here the primary heat exchanger is cooled. So if you consider how much amount of RAM air is for cooling in the heat exchanger 1, and how much amount of the exhaust from the turbine is used for the cooling in the regenerator. So that also you can find out if you know the difference between the two temperatures. For example, in the primary heat exchanger, if you take M is the mass of the rammed air used, then in that case, so you can find out M1. So that is the mass of air from the turbine is used for cooling in the regenerator also, because the exhaust from the turbine is at a temperature T6. Okay, so that will go at some other temperature, for example T8. Okay, so then what is the mass of the exhaust from the turbine is nothing but here the heat taken away by this exhaust used here for cooling the regenerator is nothing but, so if you take that as M2, so M2 into Cp into delta T. So the delta T will be some T8 minus T6. Okay, because T6 regenerator and T8 will be the exhaust of that. Okay, coming at very at other temperature T8. So whereas T7 is nothing but, so that is the exhaust of air from the cabin, because the inlet to the cabin is T6. So the exhaust to the cabin will be T7. So T8 is about the heat rejection in the regenerator. So that also you can find out. Then the last type is reduced ambient type cooling system. So you can see the reduced ambient type cooling system. So here is mainly consisting of a heat exchanger and two expansion turbines. Okay. So in between the two expansion turbines, there is a heat exchanger. So here the heat exchanger, so the exhaust from the second turbine is used for cooling the compressed air coming from the compressor. Okay. So from the main compressor, a part is used for this air conditioning that goes into the heat exchanger. Okay. Then how it will be cooled is by means of expansion of the rammed air. So ram air is expanded in the turbine 1. Okay. So that exhaust is utilized for cooling of that. Okay. Then afterwards, the heat rejected air comes from the heat exchanger again into the turbine 2, where some work is done. So that work is utilized for running the exhaust fan. So that fan will uh, uh, increase the heat transfer rate to the heat exchanger. Okay. Then at the exit of the secondary turbine, so the air will be at low pressure and temperature, which can take heat from the cabin to be conditioned. So only here the difference here is that the exhaust from the first turbine is utilized for heat rejection in the primary heat exchanger. Okay. So the same thing you can see from the TS diagram. So 1 to 2 is ramming and 2 to 3 is actual compression in the main compressor, and 3 to 4. So 3 to 4 is nothing but here the heat rejection in the heat exchanger. So that is by means of the exhaust from the first turbine itself. So that's why here the expansion in the first turbine is not given. Okay. So the work done by the first turbine is utilized for cooling the heat exchanger. Okay. Cooling required for the compressed air in the heat exchanger. Whereas 4, 5 is nothing but the expansion from the cooling turbine. Okay. That is used for running this fan. So even in this also you can find out mass of the air required, and also you can find out the work input. So work input to the compressor is nothing but MCP T3 minus T2, and also you can find out the COP 3.5 T by. So this difference between the temperatures into CP. So far what we have assumed is that the compression process and the expansion process are isentropic, but these are not isentropic, these will be polytropic also. So the efficiency of the compressor and efficiency of the turbine are also plays an important role for compression and also expansion processes. So isentropic compression, isentropic efficiency of the compressor is nothing but ratio of the isentropic work required by the actual work required. So 1 to 2 is the ideal process. So that is the isentropic process. Whereas 1, 2 dash is the actual process. That is the polytropic process. We can find out the isometric efficiency of the compressor, which is equal to, so H2 minus H1 by H2 dash minus H1. So that H2 can be written as, so MCP delta T. So that is M into CP into T2 minus T1 by the denominator is again MCP delta T. So the delta T is nothing but T2 dash minus T1. So in the same way, we can also find out the isentropic efficiency of the turbine. If we know the actual exit temperature and the isentropic exit temperature. So 3, 4 is the isentropic work done by the turbine, and 3, 4 dash is the actual work done by the turbine. So with that you can find, so the actual condition of air from the compressor and the actual condition of air coming from the turbine also. So you can find out even for the heat exchangers what is the effectiveness of the heat exchanger. So you know that heat exchangers are mainly classified into two types: parallel flow heat exchanger and counter flow heat exchanger. So you can find out the effectiveness of the parallel flow heat exchangers by knowing the temperatures for the hot fluid and also the cold fluid. So that is equal to Thi minus Th naught. So Thi is the inlet temperature of the hot fluid. So that is nothing but here air that is to be cooled. So Th naught, the air comes at a temperature Th naught. And similarly, denominator Thi by Tci. Tci is the inlet temperature of the cold fluid. And similarly, for the counter flow heat exchanger, so here one fluid is moving in one direction, the other fluid is moving in the opposite direction. So for that also you can find out the effectiveness of the heat exchanger by knowing the all the temperatures Thi minus Th naught by Thi minus Tci. So cold fluid outlet temperature is immaterial for us. What is the inlet temperature of the cold fluid? That is more important. So with that we can find out the effectiveness of the primary heat exchanger or secondary heat exchanger, or otherwise we can find out the effectiveness of the evaporator used also. So this is about the total power requirement for the air conditioning. So the total power required is nothing but the power required for pressurization and power required for refrigeration. So power required for pressurization. So how much power is required for the compressor to get the required pressure, and the power required for refrigeration. So you can see the graph showing. So the power required versus the height, that is the altitude, given in terms of thousands of meters. So the total pressure you can see almost constant. So as the height increases, so you can see that as the height increases, the power required for pressurization will be more. Okay. So compared with that of the power required for refrigeration, because at high altitude temperature will be less. Okay. And also of course pressure will also be less, but more significance is given for pressure and the temperature. So like that here almost the power required is constant, but that depends upon the altitude. So whether the total power required is mainly depending on only pressurization or mainly depending on refrigeration. So at on earth if you see, okay, so at atmospheric pressure the total power required is nothing but only for the refrigeration. Okay, with increase in the altitude, so here the power required for pressurization also increases, but the power required for refrigeration decreases. So we have seen different types of air cooling systems used for aircrafts. So simple cooling system, then bootstrap, then regenerative, then reduced ambient type and all this. So this is the graph showing Mach number versus the discharge temperature of the cooling turbine. So the main importance is always given for the lower temperature. So that is nothing but the discharge temperature of the cooling turbine. So if it is low, then it can take more heat from the chamber to be cooled, or otherwise less amount of air can be used for cooling. Okay. So the lower is the temperature, the lower is the mass flow rate required, and the more will be the heat taken away from the cabin to be refrigerated. So in the simple cooling system, you can see that so the discharge temperature is high, okay, even at lower Mach numbers also. So whereas you can see here regenerative or bootstrap system, so at low Mach numbers the discharge temperature is low. So as the Mach number increases with altitude, the discharge temperature also increases. So the reduced ambient type. So the reduced ambient type is always preferred when the Mach number is in between 1 to 1.7, where the exhaust temperature from the turbine is low. Okay. So compared with all this, the reduced ambient type is preferred even at high altitudes also, compared with bootstrap, regenerative or simple cooling system. So whatever we have seen the different types, but the actual air conditioning system requires number of controls. So whatever the controls required are the temperature control in the cabin, then the airflow control. So the quantity of air required for the controlling, and also the water separators, and also the moisture removals and all these. So all these are required to maintain the required temperature and pressure inside the cabin. So last class I have given one problem on Bell-Coleman cycle. So how many of you attempted that? So what are the answers? Hmm? So for these are very simple problems. Only it is the inlet conditions, temperature, pressure is known. Then the other, if at all some other temperature is given. So using the relations, you have to find out all the temperatures. Then only you can solve COP, or otherwise you can find out work input, anything. What is the mass of the air required and all those. So I am again repeating the problem. Have you taken the problem? So a refrigeration machine of 6 tons capacity working on Bell-Coleman cycle has an upper limit of 5.2 bar. The pressure and temperature at the suction of the compressor. So that is at 1, the inlet of the compressor, the pressure is given as 1 bar and temperature is given as 18 degrees centigrade. And the minimum pressure is 1 bar given, the maximum pressure is given as 5.2 bar. So with that you can find out T2. Okay. Then the compressed air enters the expander at 41 degrees centigrade. So T3 is also given. So that is 41 degrees centigrade. So assuming that expansion and compression are adiabatic, so with gamma 1.4, so find the COP, quantity of air circulated per minute, piston displacement, and also the power required to drive the compressor. So for all these problems, you first draw one TS diagram. Okay, if you draw a TS diagram and if you note down what are the temperature, pressure given, then you will get. So the examiner will get an impression that you know how to draw the cycle and you know what are the conditions and all those. Okay, then you will get full marks. Okay. So if you get the answers correct, then full marks will be awarded for you. So 1 is given, T1, P1 is given. Similarly, T3 is given. So with that, you find out what is the work input. So work input is nothing but work required by the compressor minus work done by the expander. So per kg of the air, you find out this. So that will be. So after finding all the temperatures, only 2 temperatures are given here. So remaining temperatures you have to find out. So T1 is given. You can find out T2. So T2 by T1 is equal to P2 by P1 to the power of gamma minus by gamma. So similarly T3 is given. Find out T4. So T3 by T4 is, so P2 by P1 to the power of gamma minus 1 by gamma. So with that you find out, then you will get T2 as 466 Kelvin and T4 as 196 Kelvin. So with that you find out work input, which is 57 kilojoules per kg of air. Then the refrigeration effect produced is during the process 4-1. So that is again Cp into T1 minus T4. So you know T1, you know T4. So then find out that. So that is equal to 1.6. COP is 1.67. Then find out the refrigeration capacity. So the refrigeration capacity is given in tons, 6 tons. Then convert that to kilojoules per kg. Kilojoules per second. You can find out. If you multiply that with 3.5, you will get this in 21 kg per kilojoules per second. Then find out mass of the air per second. So which is nothing but the refrigeration capacity by the refrigerating effect produced, okay, per kg of air. Then you will get mass of air per second as 0.22 kg per second. Then the power required. So the total power required for that tonnage is nothing but work done per kg of air into mass of the air. So already we have done that the work input is 57 kilojoules per kg. You multiply that with mass of air per second, 0.22. Then you will get the power in kilowatt. So 12.54 kilowatt. Actually mass of air required per minute is asked. So you multiply that with respect to m with 60. Then you will get 12.21 something. Then the next required here is D and L. Okay. So for that find out what is the volume at 1 and volume at 4. Because here 1 is at the suction of the compressor, the total volume required is MRT1 by P1. Similarly, piston displacement of compressor, you will get that as 11 meter cube per minute. So V4. So V4 also you can find out MRT4 by P4. That is 7.42 meter cube per minute. Then piston displacement of expander V4 is 7.42 meter cube per minute. So you know that this is a double acting one. So V1, that is the volume equal to 2 into 5 by 4 D square Ln. So D and L. So here it is given that L is nothing but 0.2 times D. So then you can find out the diameter of the compressor cylinder as 0.38 meters. And similarly you can find out V4. So that is 2 into 5 by 4 D2 square into Ln. So with that, so diameter of the expander cylinder is 0.313 meters. So that problem you can do. Then in that problem, what we have assumed is compression and expansion are isentropic. But as in the we have seen the main deviation, so compression and expansion are not isentropic. And some problems may also be there. So where the pressure drop takes place during heat addition or heat rejection. Okay? So that problems. So these are the three types of problems comes under the Bell-Coleman cycle. Take another problem on this. An air refrigerator system operating on Bell-Coleman cycle takes air at cold room at 268 Kelvin and compresses it from 1 bar to 5.5 bar. The index of compression is 1.25. The polytropic index is given as 1.25. The compressed air is cooled to 300 Kelvin. The ambient temperature is 20 degrees centigrade. The index of expansion is 1.35. So here the index of compression is 1.25 and index of expansion is given as 1.35. So you have to calculate COP of the system, quantity of air circulated per minute for production of 1500 kgs of ice per day at 0 degrees centigrade from water at 20 degrees centigrade. And the third is capacity of the plant. So initial conditions are given. So that is given as 1 bar. So the pressure is given as 1 bar and the temperature 300 Kelvin. Compressed air is cooled to 300 Kelvin. So 3 is given. So T3 is given as 300 and ambient temperature is given as 20. And 1 is given as T1 is given as 268 Kelvin. So assuming that first 1 2 dash. Okay. So 1 to 2 first assuming as isentropic process. So you can find out the exit at 2. So that you can find out as T2 is equal to T1 into P2 by P1 to the power of gamma minus 1 by gamma. So then you will get T2. Then you have to find out actual exit temperature from the compressor. So that is the polytropic process. So with the isentropic efficiency given or otherwise with the index itself we can find out that. So because the polytropic index is given, so directly you can find out T2, that is the actual exit from the compressor, is equal to T2 by T1 is equal to P2 by P1 to the power of gamma minus 1 by gamma. And sometimes instead of giving the polytropic index, so isentropic efficiency of the compressor will be given. So in that case, so first thing is you have to assume that the compression process is isentropic. First find out T2. Then find out from the isentropic efficiency of the compressor. So the actual exit temperature from the compressor. So here directly the index is given. So that you can directly substitute 1.25. Then similarly T3 is known. Find out T4. So using the polytropic index for expansion. So that is given as 1.35. Then find out the work input to the compressor. Then work done by the expander. So with the formula n by n minus 1 into gamma minus 1 by gamma into Cp into T2 minus T1. So the actual compression process 1 to 2. Then similarly the expander work. So you can find out in kilojoules per kg. Then with that you find out the net work required by compressor minus work done by the expander. Then find out the refrigerating effect produced during the process 4-1. So that is Cp into T4 minus T1. So after getting the refrigerating effect network done, you can find out the coefficient of performance. So coefficient of performance for this problem is 2. Then to find out the mass flow rate. So what is the total heat to be extracted and what is the actual heat extracted per second per kg first find out, then per second if you find, then you can find out the refrigeration capacity. So find the heat extracted per kg of ice. So here ice is required at 0 degrees centigrade and water is sent at 20 degrees centigrade. So that is, so M is not given, you have to find out. So Cp delta T plus the latent heat of ice L. So with that you can find out heat extracted per kg of ice. Then mass of ice produced. So that is here 1500 is given. So 1500 by, so 24 into 3600. So we'll give this as the mass of the ice in kg per second. Then find out what is the actual heat to be extracted. So that is M into H or the refrigeration capacity. So that is 7.26 kilojoules per second. Then find out how much tonnage is required. So by dividing with 3.5. So with that you can find out what is the total mass flow rate required. That is the total refrigeration capacity by the refrigerating effect produced per kg. So that is 0.096 kg per second. So the difference between the previous problem and in this is nothing but the previous problem here. So the isentropic processes are given. So whereas in this the polytropic index are given. So only that is the difference between the previous one and this. And the answers are also given at the end. So you can do this problem and verify. So the difference between the previous one and in this is, in the previous problem the polytropic indexes are given for compression and expansion. So whereas in this isentropic efficiency of the compressor and turbine are given. So with that you have to find out what is the actual exit temperature from the compressor, actual exit temperature from the turbine. And there will be problems on air refrigeration systems also. Air cooling systems we have seen. Simple cooling, simple evaporative cooling, bootstrap refrigeration or bootstrap evaporative cooling system. Then similarly reduced ambient, regenerated type. So you may get number of problems on that also. Okay? Because here in this only in Bell-Coleman cycle only 4 processes are there. So whereas in that case in the cooling system, so some more temperatures are to be calculated to find out the required data. So note down this problem also. So this is a problem on simple cooling system. So an air cycle unit operating on simple system is designed for the following conditions. So 7.5 kg per minute of air entering the turbine. At 4.4 bar cabin pressure. So it is entering at 4.4 bar and the cabin pressure is 1 bar. So the discharge temperature is minus 6 degrees centigrade and the turbine efficiency is 80%. So at what temperature does the air enter the turbine? How much power does the turbine supply to the fan? So in the simple cooling system, so the function of the cooling turbine is to run the fan. Okay. So whatever the work done by the turbine is utilized for running the fan. So the ambient conditions are given, then you have to find out. So here ramming effect that is not given. Okay. Then 2 to 3 is actual compression. So all pressures you have to know, ambient pressure, then ram pressure, then similarly the compressor exit pressure, then the turbine inlet pressure, and turbine exit pressure is nothing but the cabin pressure. So try this problem also, we'll solve in the next class. So any doubts in this? Any doubts? So you follow the book Refrigeration and Air Conditioning by Dom Kundwar, okay, or even CP Arora. So you can get all the flow diagrams and number of examples are also there. You see all the example problems. And only thing here is, so with the cooling systems, number of cooling systems, just the length of the problem will only increase. The same procedure, mechanical procedure, finding all those. So doubts from you. So I'll ask questions, you have to answer. Hmm? So why reduced ambient cooling system is preferred? So reduced ambient. So with change in altitude, so the turbine exit temperature is not much affected. Okay. So with altitude height, the exit temperature should be always maintained at low temperature. Then only it can take more heat from the chamber to be air conditioned. Then why simple system is not preferred?